this one be V2. It's really the EMF, but I will ignore any kind of internal resistance of the batteries. It's completely negligible in this problem. And here I put also a battery, let this be the negative side, and this be the positive side, and let the potential difference be V1. And so imagine that you know V1, V2, R1, R2, and R3. But what I'm going to ask you is, what is I1, what is I2, and what is I3? I want the magnitude, and I want the direction. When you look at this, it's by no means obvious that the current in this resistor will be to the right or to the left. It's by no means obvious. It depends on the values of V1 and V2 and on the resistances. The basic idea behind solving these problems are in what we call Kirchhoff's rules. Kirchhoff's first rule is that the closed loop integral over a closed loop of E dot dl is zero. We've seen that before. I don't know why Kirchhoff gets the credit for this. This always is the case when we're dealing with conservative fields. When you start at a particular point, you go around E dot dl, you're back at the same potential where you were before, so this must be zero, as long as you deal with conservative fields. But that's his first rule. And you can do this closed loop anywhere. You can even do it here. It would still be zero. You can do it here, also zero. You can do it there. No matter where you do it, that closed loop integral must be zero. And then there is the second Kirchhoff's rule, and that is what we call charge conservation. If it is a steady state situation, then independent of which junction you go to, the current that flows in must flow out. You can't have a pile-up of charge. That's the second rule. And I gave you a problem, 3-7, to work out, and you can look in the book how that is done. However, I'm going to work on this with you in a slightly different way than the book is doing it, which I personally like better. But it may confuse you. So I warn you in advance. You may not want to use my method at all. What I do is the following. I say, okay, I assume that there is a closed loop current here, I1. And that there is a closed loop current here, I2. Whether I make them clockwise or counterclockwise, unimportant. I could have chosen one clockwise, the other counterclockwise, unimportant. However, once I choose the direction, it has consequences, as you will see. And that's all that's running. One current like this, and one current independently like that. If I assume that, then I have automatically I am obeying the second rule, because a current that goes around, there's charge conservation, right? There's no charge piling up. So the second rule of Kirchhoff is already obeyed. So now I go to the first one, and I can start now at any point in that circuit and go around. I can go around clockwise, I can go around counterclockwise, it makes no difference. As long as I return to the same point, that integral E dot dl must be zero. I'm returning at the same potential. What is the integral of E dot dl in going from point 1 to point 2? Well, that's the potential difference between point 1 and point 2. And so let us start here, and let us go around, and we have to adopt a certain convention, namely, if we go up in potential, and when we go down in potential. Again, you're free to choose the sign convention, but I would say, when I go up in potential, I give that a plus sign. When I go down in potential, I give that a minus sign. So I start here. I could have started there, I could have started there. It makes no difference. As long as I don't start here, that makes no sense. So I start here, and I go around like this. So right here, I go down in potential, V1. So I get minus V1. Now I go with current I1 in the direction from left to right. So that means that the potential here must be higher than there. V equals IR. Potential here must be higher than there. So I go down in potential, so I get minus I1 R1. Now I go through R3. This current I1 is going down, so this has a higher potential than here, so I go down in potential, so I get minus I1 times R3. But I have independently a current I2 which is now coming towards me when I go down. And so if it comes towards me, that current would give me an increase in potential. This would have to have a higher potential than this for this current to do this. So now I climb up the potential hill, so I get now plus I2 times R3. And we're... Uh-oh, look what I did. I wrote down I1R. There is no capital R in the whole problem. I clearly meant I1R1. So read minus I1R1. Sorry for that. No. I'm back where I was, because these wires have no resistance. And so I'm back where I am, so this is 0. One equation with two unknowns, I1 and I2. So now, let's go around this one. We can go clockwise, we can go counterclockwise, makes no difference. Let's start here, and I go in this direction once around. So now, I go through R3, and this current I2 is running in this direction, so I go down in potential. So I get minus I2 times R3. But current I1 is coming towards me. If I go in this direction, I1 is coming towards me, so I climb up the potential hill. So I get plus I1 times R3. Now I go through R3 in this direction. Current I2 is also in this direction, and so this must have a higher potential than this. So I go downhill in potential, so I have minus I2 times R2. I come down here, here's a battery, and it goes up in potential, so I get plus V2. And that's 0. Two equations with two unknowns. I can solve for I1, and I can solve for I2. So I1 and I2 pop out. Let us assume that I1 is positive. I find a positive value. It means it's really in this direction. Let's suppose that I1 is negative. I find minus 3 amperes. Well, it means that I1 is in this direction. Big deal. And so the whole operation is sign sensitive. And the same is true here. If I2 is positive, it means it's in